here we are. We're recording to the cloud, and then I'll post it. Just a reminder, final next week, blah, blah, blah. You can read all this. You don't need me to read it out loud. You are adults that are educated. And so what we want to talk about today is we want to talk about solving a system of congruences. And then also we want to talk about a little trick due to the famous mathematician, philosopher, Pierre Fermat that helps us do these things. All right, so when we're talking about solving congruences, there's two important questions. Can we solve this? And we already discussed this. We know that it has a unique solution when there's this property between A, B, and the modulus, and we talked about inverses, and hopefully you've worked on that, or at least read about it and given it some thought. So, and then if we go to the next page, the other question that we haven't discussed, well, maybe you've read about it, is can we solve a system? So what would a system look like? Well, if it's two equations, it might look something like this. X congruent to, say, B1 mod, we'll call it M sub 1. And then we might have X congruent to some other integer, B sub 2, modulo some integer, M sub 2. And in theory, we might ask this for, say, N equations, or I guess I should be more specific, N congruences. So the question is, can we solve this? I've alluded to this many times. These types of questions are interesting from a math nerd perspective. In fact, a problem like this on the screen, we have evidence that this dates back to antiquity, long time ago. And in fact, the theorem that allows us to systematically solve these types of things in many cases really dates back a long time ago. And in fact, in honor of where it appeared in, well, not maybe the first place, I guess it is historically the first place it appeared. It's called the Chinese remainder theorem. And this dates back to the 1st century. So these kinds of questions have interested people for a long time. And it turns out in our modern world, they still have many uses. And as I've suggested, one of the main uses of all this stuff is digital things like digital security, encryption. Okay, so here's where we're at. We want to solve something like this. Now, you guys have encountered systems before. You absolutely did it in an algebra class. You usually would have studied maybe 2 equations and 2 unknowns, or maybe you solved 3 equations and a few unknowns. But what we're asking for here is, does a solution exist? Is there a number X that satisfies all this? And more importantly, if so, is the solution unique? That's an important question in many applications. So what we're going to do is we're going to leave this scary symbols right now, and we're going to look at a concrete example, and we're going to think about how we might solve it. Does anybody have a comment or a question? Oh, here we go. Someone wants to say something. Yes. What is your comment or question, Jared? Or do you just want to say yes because it's the last class? Well, right. If there's 17 numbers that work, then there's going to be, sure, absolutely. Look, part of the reason uniqueness is important is not necessarily that we always want a unique solution. Oftentimes, it's beneficial for us if there aren't unique solutions, that there's multiple solutions. Because imagine you're using this as an application for something, you might want more than one choice. As you suggest, optimization for sure. Uh, Yet there are other times where it's important from an application standpoint that a solution is unique. Because once we know that we have a unique solution, if the theory tells us it's unique, that means once we find one, we're done. We can end the search, so to speak. And that has many important consequences, as you would imagine. Suppose we are, one of the applications the book goes into is it explains to you how serial numbers work, and like, for example, ISBN numbers, and how there's lots and lots of different examples we can give, but the book goes into these things, and some things you might be familiar with, like hashing functions. And so it's important when we're doing these things, if we understand when something has a unique solution and when it doesn't. I mean, it'd be a shame if you go to the grocery store, for example, and those barcodes that are on something you purchase, it would be a shame if the two different barcodes on two different products actually registered for the same product. I mean, that would not be ideal if you're trying to keep inventory and you're trying to operate your grocery store. So sometimes uniqueness is important and sometimes it's not. So from a math nerd perspective and an application perspective, we'd like to know these things. So the question that you pose is a good one. Yeah. So here's a cool thing about this. There's a big theorem that tells us how to do it, and it's called the Chinese remainder theorem. So the Chinese remainder theorem provides not only a theoretical tool, but provides a method for finding, so to speak. Finding's a weird word to me because it ain't lost. But the Chinese remainder theorem provides a method for finding a unique solution under certain hypotheses. So as you would imagine, these hypotheses are going to have to do with some of the things we pointed out to earlier. That we know that a solution exists unique for one congruence, given that there's an inverse. And there's also, in order for there to be an inverse, we had to have this notion of two things. We had to have this idea of relative primeness going on as well. So if the moduli M1, M2, M3 up to M sub n are relatively prime. Now, that we have to think of it in a pairwise way. And if that's the case, we have a unique solution. And not only is it unique, this is a cool theorem. The reason the Chinese remainder theorem is a cool theorem is because not only does it tell you that there is a solution, it tells you how to get it. Now, I know that that's often lost on some of us at this stage in our math education, but if you go to certain classes, like those of you who have had calculus, there was a couple theorems that you studied. One was called the intermediate value theorem. One was called the mean value theorem. And these theorems were what we call existence theorems. They tell you something is there, but the theorem or its proof do not tell you how to find it. So from a theoretical standpoint, that's very important because we know something's there. But from a practical standpoint, well, what good is it? If it's out there and I don't know how to get it, what good is it? So what's interesting about this theorem is not only does it tell us something exists, it also tells us how to get it. And so that's pretty cool. So what we're going to do is we're going to illustrate it on the case of three equations, or excuse me, three congruences. So is not to confuse or to have what I like to call messy notation. Let's look at an example of three congruences. So we're not going to do n. So what would three congruences look like? It would look like x congruent to b sub 1, where b sub 1 is some number, mod m1. X congruent to b sub 2, mod m sub 2, and then x congruent to b sub 3, mod m3. So for example, on the homework, I gave you a problem. Heck, I don't even remember what it was now. I think b sub 1 was like 1, b sub 2 was 6, and b sub 3 was 3 maybe. And then the moduli were 5, 6, and 7. So what we're going to do is you assume the GCD of M1 and M2 is 1. You assume the GCD of M1 and M3 is 1. This is what pairwise relatively prime means. And you assume that the GCD of M2 and M sub 3 is equal to 1. Now, this assumption is going to be important because this assumption tells us that an inverse exists, and it also then tells us that we get a solution for one congruence. And so what we're going to do is we're going to build our solution using some sort of creative reasoning. Okay, comments, questions? Okay, going once, going twice. Sold. All right, so let's have at it then. Move this. No room on the desk up here. It's frustrating. Okay, so look what we can do now. We can make some sort of moves happen. So set. I'm going to use this notation because this is, I believe, what the book uses. So I'm going to set capital M1 to be equal to, well, I guess let me start a little slower. Let's build it up. So define a new moduli. So we're going to define m. If I can write m, which apparently I can't. So how am I going to define m? I'm going to take my 3 moduli and multiply them together. So if we take these 3 numbers, we can multiply them together. We get a new number, which we're going to call m. And now I'm going to take and define a new number, which is capital M. And that's going to be equal to little m divided by little m1. Of course, another way of writing this is you can write this as m sub 2 times m sub 3. Then we're going to take capital M sub 2, which is little m over m sub 2. And of course, that is m sub 1 times m sub 3. And then m sub 3, which is going to be little m over m sub 3, which another way of writing that is m sub 1 times m sub 2. Okay, so what good is all this? Well, let's look at the GCDs. And this is important to understand. We're constructing this in this way. So what is the GCD of, say, little m sub 1, comma, capital M sub 1? Well, that is 1. And then the GCD of lowercase m sub 2 with capital M sub 2 is 1. And then, of course, the GCD of lowercase m with capital M is also 1. Now, why is this of any importance? Well, what this does is we had a theorem that we stated, and this tells us that certain inverses exist. So this tells us that write it in red. This implies that inverses exist. Now, exactly what inverses am I babbling about? In particular, we can take capital M sub 1. It has an inverse, which I'll call y sub 1, mod lowercase m sub 1. And then we have an inverse for capital M sub 2, which we'll call y sub 2. This should be congruent. Mod lowercase m sub 2. And then last but not least, the third guy. The third capital M has, or excuse me, m sub 3, I guess is the correct way of saying it. It also has an inverse. Mod m sub 3. So I'm not pulling any of this stuff out of thin air. I'm constructing this. I'm saying, okay, let's look at what we can do. Given our assumption of relatively prime, what can I do? Well, I can find these values. Now, it's going to seem lost on you right now. First off, there's lots of symbols here, and I understand that's overwhelming. But at some point, that's part of learning how the general ideas work. You have to be able to do something in an abstract manner. Now, oftentimes, it's easier to do a concrete example first than the abstraction. And I try to balance that. Those of you who have had me in class, I try to do that. I try to sometimes do concrete, then abstract. Here we're going the other way. We're going to do abstract, then concrete. But one of the skills that you should try to sort of get better at as you grow in your, as a student, and more importantly, not as a student, but as a learner, is you have to understand that abstraction is difficult, but it is important that you can not only go from abstraction, like what you see on this screen, just a bunch of symbols that look overwhelming, going from abstract to concrete and back. That's really one of the bigger themes of a course like this, is being able to get good at that. And the problem is that's not easy to do. So most students look at this page, you look at this page, and it's just overwhelming because you're like, what are all these symbols? Oh my God. But I think it is worth your while to attempt to understand this. And of course, we'll do an example in about 5 seconds. Well, maybe like 35 seconds. Okay, so here's what's pretty cool. What's cool is we can now think about, if a solution is going to exist, what would it look like? Well, if we go back to the original problem, if a solution exists, we know that this has to be true. We know this has to be true. So if a solution is going to exist, then at some point, we know that the remainder when we divide it by m sub 1 has to be b sub 1. We know the remainder when we divide it by m sub 2 has to be b sub 2. So we might think about, okay, if something is going to work, what the heck does it have to look like? And it turns out, if you play around with that, if you say, okay, we know not every number can be a solution, so let's ask ourselves, what would a solution look like? Now, that's not easy for us as amateurs to do, but if you suffer and take out a writing instrument and play around with it, and then trial and error, and then say, okay, I did this for 10 minutes and it makes no sense. I did this for half an hour and it makes no sense. That's part of learning. But at some point, if you keep digging at it, you'll say, you'll have that epiphany that you need. And the key is you say, okay, if we're going to have something that, think of this in terms of the theme of science and not even just math. If something's going to work for the first congruence, the second congruence, and the third congruence, then maybe the solution itself is built from a piece that works for all three. And so since we're dealing with numbers, there's really two ways to think about it. If I'm going to build a solution, would it be maybe multiply something that works here times something that works here times something that works here? And if you try that, you realize that's not going to make sense. So it turns out the sort of thing that works here, the magical sort of connection is, okay, find something that works here, find something that works here, find something that works here, and add them together. Now, when I say find something that works, we don't mean a specific solution, because a specific solution here is not necessarily going to make this work or the third one work. So what we have to do is we have to construct something that works. And anyhow, it turns out that the following does work. So the big thing about the Chinese remainder theorem is this works. So the sum x equals b sub 1 capital M sub 1 y sub 1 plus b sub 2 capital M sub 2 y sub 2 plus b sub 3 capital M sub 3 y sub 3 is our unique up to modulo M solution. So the thing to note is if you take modulo M sub 1, little m sub 1, these two disappear. They're zero. And then if you go down the line, so the thing is we found something that works for the first, find something that works for the second, find something that works for the third, and add them together. And it turns out, as maybe intuition would either tell you it should or shouldn't, who knows, it turns out when you add them together, it works. And that's always good. How do we know that? Well, you could check. You should verify it. That would be good practice for you. Okay. Let's see an example. Does anybody have a question? Comment? Woo. Is everybody alive in there? Is everybody sleeping? I shouldn't say alive. That's not nice to say.
We're alive.
You're alive. Hi, Mackenzie.
Hi.
How's life? But again, it's stressful, huh?
Sorry.
Yeah. You guys all going to listen to the authorities and lay low for you're sleeping, dear. Very good. What do you mean, Carly? You wish you were alive or no? What's happening here?
No, I'm going to South Carolina.
Oh my God. Are you going there to go back to court or wherever the hell you were going, fighting with these people?
No, I took the dog back because she was freaking out of her mind.
I can't believe you better be careful with them dogs going across state lines. That got Michael Vick in big trouble. Just saying. By the way, I got this book, and I figured I'd share with you. It's not really math. It's called On Bullshit. It's pretty interesting. You should read it. It's a tiny little thing. It's like philosophy. It's really good.
What is it?
Called On Bullshit. You shouldn't swear, but just imagine bull poop. It's a good book. It's really good. It's like a philosophical book. And then this other guy, I shouldn't say a guy, I believe he's an epidemiologist. Where did I put that? He wrote a book sort of like as a rebuttal, not a rebuttal, but like, here it is. And this guy, Carl Bergstrom, and I guess I don't know who Jevin West is, he wrote a book called Calling Bullshit. This is pretty good, especially in the time of the Roni and all the, as Trump calls it, the fake news. Anyhow, that's a nice break from math for a second. And then, it's pretty good. They teach a class on this, I believe, at the University of Washington. It's really called Calling Bullshit. I should write a class called Calling Bullshit and see if LaRoche will let me teach it. You know how much fun that would be?
LaRoche would never.
Yeah, they might. By the way, that can be with geometry, as we'll call it geometry in the spring, but it'll really be calling bullshit.
Me, please. I don't want to learn geometry.
Yes, you do. You want to teach math, you numbskull. You absolutely want to learn geometry.
I learned it before. I don't need to do it again.
This is different.
I'm learning it for you too.
What's that? You're learning what?
And I'm relearning that class so that she can have it.
There you go. That's right.
Directed study.
That's precisely how life should be. Yes. All right. Let's do an example of this. I actually worked one out. So before class, I was thinking it only took me 6 minutes to do it. So this is nothing for you guys. It should only take you 10. All right. So let's do an example.
You've been studying this for how long?
Well, I mean, I don't know. I probably haven't solved one of these in 2 years. I haven't taught this class since 2018. So, I mean, I forget things as well. So let's solve the following system. X congruent to 3 mod 5. X congruent to 1 mod 7. And by the way, I think, Michelle, this is I sent you a link to a video. I don't know if you watched it, but this is the problem I believe she does. I'm not positive. I think this is what she does. Maybe not. I don't know. I thought that was a good link, but my perspective, did you learn anything from it? I have no idea if you learned anything from it or not, but I'm going to resend that link to the class because I tend to think both of those videos are good, but my perspective is biased because I sort of already know this stuff, you know? So let's solve this particular creature. Now I'm going to solve it. I think that Jay, I think she's a pretty good explainer of these things. She has a lot of good math videos. She sort of explains it a little different than I'm going to explain it. So maybe you guys can compare and contrast methods. Plus she has a British accent, so that's always cool. Is that culturally insensitive to say that? I don't know.
No, I don't think so.
I don't know. I'm just curious. Okay, so here's what we know. So first off, here's the first way you think about this problem. So the first thing to note is that the GCDs of the moduli are, in fact, pairwise 1, or so, oh, excuse me, the GCDs, if I take all the moduli, are 1. And so that means in fancy talk that that they are pairwise relatively prime. So this means the Chinese remainder theorem guarantees a solution that is unique. So the only way the Chinese remainder theorem works is if I can't do what I did before if I don't have this scenario. So you look, if you want to use a tool, you have to make sure the hypotheses are met and that the tool is applicable. So in mathematics, that's what it means. We got to make sure the scene is the stage is set, as they like to say. Okay, so very good. Now we just have to do this construction that we did before. So the construction we did before is we defined these new numbers. So the first thing that we'll do is take little m. Little m are the moduli multiplied together. 5 times 7 times 8. Now, honestly, I don't care what this number is at this moment. You could multiply it out if you wanted, but I'm not going to. And now I'm going to construct my m sub 1s. My capital M sub 1 is, and by the way, if you guys love to do this when you're learning, so maybe I'll do it for you. 5 is, for comparison, that's m sub 1. 7 is m sub 2. And 8 is little m sub 3. So maybe I'll be very careful with how I distinguish my lower cases from upper cases. Trying to make my upper cases not round, but sharp. So this becomes 7 times 8, which is 40. Capital M sub 2 becomes 5. Jeez, I'm losing my mind. Now I'm flunking. 7 times 8 is not 40, it's 56. Heavens to Betsy. This one is 5 times 8, which is 40. And capital M sub 3 is 5 times 7, which is, of course, 35. Does anybody have a question? Okay, so this is the first thing we do. We construct these numbers where we're going to have our new modulus, which is going to be used for our solution, and that is 5 times 7 times 8. And then what we'd like to do is we're going to build up how we solve each piece. There's 3 pieces. So the corresponding congruences that are connected with these 3 are, we're going to use this right here. So let me get a different color. So these give the following. Use a dark green. So we need capital M sub 1, lowercase y sub 1, congruent to 1, mod M sub 1. And then we need capital M sub 2, y sub 2, congruent to 1, mod M sub 2. And then, of course, we need capital M sub 3, y sub 3, congruent to 1, mod lowercase m sub 3. But, of course, we don't care about it in these letters. We need the corresponding values. So what are the values? This is 56y1 congruent to 1, mod 5. This is 40 congruent to, or excuse me, 40 times y sub 2 needs to be congruent to 1, mod 7. And then last but not least, we know that y sub 3 exists as well. We just have to figure out what it is. And this is mod 8. Now, this is the step that's usually the most difficult for students, because now it's not just writing down and memorizing a formula. Now you have to use your brain. The memorization part is over. Now you have to reason what these y sub 1, y sub 2, and y sub 3 are. And we know they exist because a theorem we talked about last week tells us they exist, but now we have to figure out what they are. So probably the best way to do this, at least in a class setting like this, is to, well, I guess if you know how to use technology, you can have a computer tell you what they are, but let's assume we don't. We need to figure out what number do we multiply by 56 so that when we divide by 5, the remainder is 1. So probably the easiest thing to do is trial and error. Start with 1, then 2, then 3, then 4, etc. until you get it. So in theory, you only have to, well, it's not saying theory. So if you start at 1, take 56. Well, when you divide 56 by 5, you get 1 as a remainder. Think about it. What is 56 minus 1? 56 minus 1 is 55, and that is divisible by 5. So we get, we have to solve these things. These are usually the only really hard part of the problem, or the thinking part. We need to reason what these are. So you do one at a time. Ask yourself, what number do you multiply 56 by so that when you subtract 1, it's divisible by 5? And the answer is 1 works. So you get that y is congruent to 1 mod 5. So I hate going, I don't want to go to the next page because I want you to see it, but these things, so now we're kind of going this way. These imply that y is congruent to 1 mod 5. And again, if you can't see y, let me explain, and I'm going to erase. Why? Because 56 minus 1 is divisible by 5. Now, does anybody have a comment about that?
Can you get back to the previous page for a few seconds?
Sure.
I just want to look.
Let me know when you're good.
You're good.
By the way, while I'm on this page, it's worth noting that a system this small, just 3 congruences, you might be able to reason the solution without doing all this. You might be able to trial and error yourself through it. The thing is, though, is unless you have a systematic method, how do you generalize it to 10 congruences, 100? How do you program a computer to solve it for you? Do you understand? So that should be something that you think about as well. This Chinese remainder theorem sort of gives us an algorithm that we can use to solve, even though it might be redundant on simple systems. In the general setting, it might not be. All right, so let me erase this real quick. This is sort of poor penmanship. So this is mod 5. Okay, now we need to use similar reasoning to get what y sub 2 is. Well, let's ask ourselves, what happens when we take 40 minus 1? Is 39 divisible by 7? No. Is 80 minus 1? Is 79 divisible by 7? The answer is no. What about 120? If I take 120 and subtract 1, I get 119. Is 119 divisible by 7? And the answer is yes. 119 is divisible by 7. So since 119 is divisible by 7, that tells us that y sub 2 must be congruent to 3 mod 7. And then lastly, we need to reason about y sub 3. We play the game again. Is 34 divisible by 8? No. Is 69 divisible by 8? No. Okay, so what's 3 times 35? So let me show you one way you could do this. If I go back to the internet, what is 3 times 35? Well, that's 105. And so if I subtract 1, I get 104. Is 3 times 35 minus 1, is that divisible by 8? And the answer is yes. 8 does divide 3 times 35 minus 1. So since 8 divides that, 8 divides 3 times 35 minus 1, that tells us another way of writing that, an equivalent way is saying that y sub 3 is congruent to 3. Mod 8. So now we have our capital M's and we have our Y's. And so now we can tell you what the solution is. We just have to use the proper formula. And what formula is it? It's what the Chinese remainder theorem tells us. B sub 1, capital M sub 1, Y sub 1. And add up all the similar or the analogous ones. And so if we go to the next page, the solution is x equals b sub 1, m sub 1, y sub 1, plus b sub 2, capital M sub 2, y sub 2, plus b sub 3 times capital M sub 3 times y sub 3, which in this particular problem is 3. What was capital M sub 1? We already know what that was. That was 56. Y sub 1 is 1. Then it was 1 times 40 times 3 plus 6 times 5 times 7, which is 35, times 3. And so if you go to a calculator, you get that this is 918. Now, we need to note what the Chinese remainder theorem tells us, though. So perhaps I wasn't clear with that, and I should have been. If I go back here, I was. So this is our solution modulo M. So what we need to do now is we need to recognize that our solution must be congruent to 918 mod M. Now, what was M? Well, M was the 3 moduli that we started with. And so if you go do the arithmetic, that means you take 5 times 7, which is 35, times 8, and you get 280. So you need to figure out what is 918 mod 280. Or other words, what is the remainder when you divide 918 by 280? So the first thing you do is ask yourself, how many times does 280 go into 918? So you're probably going to need a calculator for that. So you might say, okay, what's 280 times 3? Well, I get 840. And so 918 minus 840 is 78. So is this the correct answer? So here's what I'm reasoning a certain way. I'm using a calculator. So over here, what I'm saying is I'm saying that 918 is 3 times 280 plus what was the remainder? 78. So that tells us then that this thing is congruent to 78 mod 280. That's provided we didn't make a mistake. And one way to think about did we make a mistake is we check. We can check that the solution works. And we'll do that in a second. But the first thing I want to do is check my arithmetic over here. So I'm going to go to a calculator. And please ask a question if you want, if you're curious. If I take 280 times 3 and I add 78, I better get, uh-oh, that's not good. Oh, hit the wrong button. It should be 2. Sorry. This is 280, sorry. I get 919. So my arithmetic does check out. Look, this equation up here, 280 times 3 plus 78 equals 918. That tells me that 918 is congruent to 78 mod 3. Or excuse me, mod 280. So the only thing left to do is check this number works for all three. So down here, I'm going to write check. Is 78 congruent to 3 mod 7? Well, take 78, or excuse me, mod 5. Well, 78 minus 3 is 75. 75 is clearly divisible by 5. Is 78 congruent to 1 mod 7? Well, 78 minus 1 is 77, so that clearly checks. And then the third congruent that we needed to solve was, is 78 congruent to 6 mod 8? And 78 minus 6 is 72. 72 is clearly a multiple of 8. And so we check it off. 9 times 8 is 72. So we've solved it. A lot happening here. So if you have a comment, please speak. It can be about anything. If you have a question, it can be about anything. Please ask. As I clear my nose very unprofessionally, and I apologize for that. I'm down in my downstairs. It's cold in here. I'm cold. I'll put my hood back up. Keep my ears warm. Yes, Fink, what's your question? You don't have to say you have one. Just belt it out. Either type it or say it.
Everyone just speak out like I do.
Yeah, that's right. To be like my kid, that's all I hear Lydia upstairs. She just talks whenever the hell she wants. She's doing kindergarten upstairs. They're being home right now too.
So my question, I understand how to run through the Chinese remainder now better. But once again, I'm sorry, how do we recognize that that's the appropriate one to use?
What do you mean the appropriate one?
Well, I mean, if it's how we find the solution or not.
Oh, well, so right now, okay, here's a good way to think about it. If your question is, if I'm interpreting correctly, you're going to say, how would I know to use this? Well,
yes.
what is the only other tool? Hold on. Excuse me. What's the only other tool we've showed you to solve solutions of, excuse me, this is the only tool we've given you for solving simultaneous equations or a system, right? We haven't talked about, I mean, you could reason it any other way, but the best answer I can give you is, the real life answer is, when is the Chinese remainder theorem applicable? When these moduli here, here, and here are pairwise relatively prime. Then it's applicable. In this class, it's the only thing I've shown you. So I'm not going to ask you to solve a system of congruences that can't be solved this way. Do you understand that?
Oh, got it. Okay.
Now, of course, if you read the book, they'll show you there's other ways of doing this. You can reason it differently. One way to solve this is to reason it, they call it back substitution. So you look at one congruence and you say, okay, what does this force X to look like? And then you plug it into the other two, and then you get what the solution has to look like. But it's an equivalent method. It's just two ways to get to the same place. Do you understand what I mean?
I think I do, yeah.
So you have two ways to think about your question, Fink. One, it's the only thing we've talked about, so you use it. Two, you can use any method you want. Look, if you get the correct answer, we don't care how you got it. Now, if I ask you on the test to use the Chinese remainder theorem, well, then you should use it, right? You know, but there's definitely apps on the internet and on your phone that can do this for you. You just have to know how to find them and use them. You can also easily, it's not difficult to program a computer to do this, by the way. So those of you in computer land, you should think about, can you do it? All right, any comments, questions about this problem? Give me 1 second, I want to blow my nose. Okay, pardon me. All right, so someone's chatting it up. I like it. More drawings. You guys are funny. She's busy right now. She's up there learning her ABCs or now. What are they doing? They're learning words. I'm actually impressed what they do in kindergarten. I didn't realize she can write sentences and stuff now. Pretty good. All right. Okay. So now we want to move to a different topic. By the way, here's a cool thing that you might not have thought about with this Chinese remainder theorem. So here's another application of this that's not just for systems. So here's an application. So oftentimes we have to solve something like so AX congruent to B mod huge number. So here's a basic example with not so huge number. Say we want to solve 17x congruent to 9 mod, say 276. So what the Chinese remainder theorem does is it says, okay, cool, let's factor this modulus, and then we'll turn one equation into a system. Does that make any sense? Maybe it does, maybe it doesn't. I don't know. So if you use the prime factorization, you can rewrite as a system and use the Chinese remainder theorem. So what do I mean by that? Well, note 276 is the same as if you take its prime factorization, it's 3 times 4 times 23. Well, yeah, there's a connection with that. Linear programming is huge in the modern world, especially with optimizing, as you suggest. You can learn all about that in linear algebra. So, okay, so since 276 are these 3 primes, then what we can do is we can write our system. So you need to convince yourself of this. We don't have enough time for me to do it for you. So solving what was it, 17x congruent to 9 is equivalent. You should convince yourself why. it's equivalent to solving this system. 17x is congruent to 9 mod 3. 17x is congruent to 9 mod 4. And then 17x congruent to 9 mod 23. So this is a system. And so now apply the Chinese remainder theorem. So as I suggested, and it's unfortunate because of the corona, we're not going to get to it because we, maybe I'll try to get something up for you if you're interested. I wanted to give you a little insight into encryption. But the idea is, if we go back to the previous page, oftentimes we're solving AX congruent to B, where perhaps A and B are really huge numbers and the modulus is massive. In particular, one of the ways that RSA encryption works is this number here is a huge number, but it only has 2 factors, and they're both massive primes. And so if you think about that, you might understand why these ideas we're talking about can be used not just for fun math problems, but also for real-world applications. Okay, nonetheless, what we'd like to do before we finish, because we only have a few minutes, I feel bad, this is sad, it's our last class, I want to cry, is we want to talk about what's called Fermat's little theorem, because it offers a shortcut for solving, not solving, but reducing down moduli. Yeah, that's good. Tears are good. Tears of joy? No. So, okay. So our last theorem is a great tool for doing certain calculations. So we'll just say for calculations. Here's an amazing fact, theorem, and this is Fermat. So let P be prime and assume P does not divide A. Here's a cool fact. What this says then is A raised to the power P minus 1 is congruent to 1 mod P. So reducing things modulo P is very, very important in applications of this stuff. And so here's an awesome formula that makes it pretty straightforward. So if you think about the problem on the homework that I gave you, I think it's the last problem. Let me pull it up. Well, let's not do that. We'll steal the fun from you. Let's do a different problem. So I want to take all the joy from you. Here we go. Gotta think of a good one. Yeah. That's true. So let's look at a couple simple examples. First off, let's do one that's obvious. Take, for example, 6. 6 to the power 11 is congruent to 1. Or not 6 to the power 11, say 6 to the power 12. Is congruent to 1 mod 13. 5 to the power 22 is congruent to 1 mod 23. Notice that the key observation here is that the power is 1 less than a prime number. The power is 1 less than a prime number. So this can be used to help do some calculations. So if we look at the homework that I gave you, the very last, and this can be used in lots of places. It doesn't just have to be sort of used on this problem, but we'll change the wording around to match so you don't have to do the same one. So let's determine the remainder when, say, 2 to the power 356 is divided. So this is example 1, 2, here's 3. Divided by, how about we look at 11. So one way to do this problem is to use Fermat's theorem. So the idea is to figure out powers of 2. Well, what's 1 less than 11? Well, 1 less than 11 is 10. So what I want to do is I want to look at powers of multiples of 10. So here's what we're going to note. Note 2 to the power 10 is congruent to 1 mod 11 by Fermat's theorem. Now, if we go back a page, we're not interested in 2 to the power 10. We're interested in 2 to the power 356. But this, we also have that if I take 2 to the power 10 and raise it to the 30th power, that's congruent to 1 mod 11. And that is also not by Fermat, but that is by basic congruence theorem. We talked about that last week. So this tells us then that 2 to the power 300 is congruent to 1 mod 11. And so from this, and I don't want to steal all the thunder, so and we're out of time. So can you reason? And so I'll write it like this. It remains to reason a 2 to the power 56 in there using congruences. So we talked about it. We stated it last week that there's these two results. If you have a congruence, then you can multiply, quote unquote, both sides by something. And so what can you do? Well, you can multiply both sides of this by 2 to the 56, and then all you have to do is reason 2 to the 56. So there's a few more minutes left, so let's just do it. Does anybody have a comment? If you need to go, feel free to go. I feel bad, but I'd like to finish this problem if you want to stick around to hear the end of it. So what this tells us then is 2 to the 356 is congruent to 2 to the power 56 mod 11. But this is, as you know, this is equal to 2. If you want to think about another way of thinking about this, is 2 to the power 50 times 2 to the 6th mod 11. And because 50 is a multiple of 10 by Fermat, this is congruent to 1 times 2 to the 6th mod 11. And this is by Fermat, or Fermat. And now all you have to do is reason, how do you get 2 to, by the way, I'm not saying this is the quickest way of doing it. what is 2 to the 6th? Well, 2 to the 6th is 64. So what is the remainder of 64 when you divide it by 11? Well, 11 times 6 is 66. So take 5 in there, you get 55. So this is congruent to 9 mod 11. So if you have a question, now's a good time to sort of ask. Maybe you saw an error. I don't know. Maybe I made an error. I don't think I did. But stranger things have happened. Does anybody have a question about this? Comment. And by the way, I'm not saying this is the only way you could have reasoned it. You might have been much quicker than I was. If you go to the previous page, maybe you spot, I'm sorry, in the original problem, maybe you spot oh boy, what happened? Did I just lost everything? Maybe you spot a better way of breaking this exponent up. Maybe you say, okay, I know I can use, so alternatively, here's a quicker way of doing it. If you're still around. Ooh. Quicker way, maybe? So 2 to the 356 is the same as 2 to the power 10. And then that would be 35th power times 2 to the 6th. So you need to reason your exponents there. So of course, this is just congruent to 1 times 2 to the 6th mod 11, which as we just said is congruent to 9 mod 11. So I used Fermat here in this step. I only used Fermat once. So it's all about recognizing how to break up the power. And you need to take advantage of, I wanted to break it up into a power that is 1 less than this modulus that I was interested in. All right, we are out of time. I appreciate you guys if you stuck around. And I'm sad that this has ended. I feel bad, but you know, all good things must come to an end. Do not be afraid to contact me for anything about homework, quizzes. We're going to give you a couple more. Think of them as point getters, not stress givers. And then we'll have our final. So if you need anything, let me know. Otherwise, I will speak to you guys sooner than later, I guess. Okay. Yeah, you guys have a good holiday too. Please be safe. Make good decisions. Stay out of the police blotter. I'll see you guys. Thank you very much and have a good holiday. And I look forward to hopefully hearing from you guys over the next week or two with questions. So, take care, everybody. It's been fun. Bye now.